Hello children, how are you all? Hope you all are fine. Yeah, I am seeing your homework. Very good. You are writing the assignment. Very good. Okay. Right. In metallurgy, in previous class, what we have seen? We have seen about extraction of crude metal, isn't it? We have seen about extraction of crude metal, okay? It is carried out in two steps, okay? Conversion of ore into oxides of metal and reduction of that metal oxides to element metals, okay? We have seen detailed, okay? Now, in metallurgical process, there are three processes, isn't it? Concentration of ore, extraction of ore and refining process, okay? Today, we are going to see about refining process. Before going to refining process, we are going to see two main important topics in this lesson, okay? That is thermodynamic principle of metallurgy, okay? Which is expressed by Ellingham diagram, okay? And electrochemical principle of metallurgy. Thermodynamical principle of metallurgy is explained by Ellingham diagram and electrochemical principle of metallurgy is explained by Hall-Héroult process. Further, we will see about refining process and the applications today. Okay children, take your book, okay, take your physics book, take your chemistry book, take your chemistry book, the first volume, okay, and a note, a pen, pencil, everything you should be having with you during your class, okay, right? Okay, let us start the lesson today. Now, thermodynamic principle of metallurgy, thermodynamic principle of metallurgy, okay. As we discussed the extraction of metals from their oxides, isn't it? We have seen in the previous classes the extraction of metals from their oxides. It can be carried out by using different reducing agent, isn't it? Reduction by carbon, reduction by hydrogen, reduction by the metal, like that we have seen. So, for example, consider the reduction of metal oxide as MX and OY. MO, M is the metal, O is the oxygen. So, that is the metal oxide, okay, that is the metal oxide. So, MXOY consider as a metal oxide, okay. Now, you are converting that metal oxide to a metal plus O2, okay. O2 is expelled, that is the metal, okay. This principle is used in thermodynamic principle of metallurgy, okay. What is thermodynamics? It deals with heat, okay. It deals with heat, okay. In thermodynamics, it is a branch of physics, okay. It is a branch of physics. There is a suitable reducing agent is selected based upon the thermodynamic consideration, okay. Based upon the thermodynamic consideration, a suitable reducing agent is used, okay. So, we have to think this is a spontaneous reaction, okay, based upon a reaction. If it is a spontaneous reaction, we have to use another reducing agent. For another reaction, we have to use another reducing agent. So, in this thermodynamic principle of metallurgy, we are taking Gibbs free energy function, okay, del G, which is denoted by del G, okay, Gibbs free energy function, okay. The change in Gibbs free energy del G equal to del H minus T del S, del H minus T del S, that is the Gibbs free energy, okay. See in page number 10, how the reduction is carried out with carbon. Here, carbon is taken as a reducing agent, okay, which is oxidized to carbon dioxide, okay. Carbon plus O2 gives CO2. Carbon plus O2 gives CO2, okay. Now, we are taking carbon monoxide as a reducing agent. We are taking carbon monoxide. So, CO, 2CO plus O2 gives 2CO2. So, based upon a choosing of reducing agent, this thermodynamic considerations are taken place, okay. Del G equal to del H minus T del S, where del G is a change in Gibbs free energy, change in Gibbs free energy, and del H is the change in enthalpy, and T is the temperature which is in Kelvin, and del S is the entropy change. Okay, that is the entropy change. It is a relation founded by Harold Ellingham, founded by Harold Ellingham. Okay, he used the above relationship, the relationship del G not equal to minus RT ln Kp. Okay, he used that relationship to calculate the del G values at variable temperatures for the reduction of metal oxides by treating reduction as an equilibrium process. Okay, the main aim is to reduce the metal oxide. To reduce the metal oxides to metal, we are using a what? A reducing agent. Okay, for that they are calculating based upon the Gibbs free energy, that is called thermodynamic equilibrium. Thermodynamic principle of metallurgy is determined. Okay, okay, what he has done here, let us see. This Harold Ellingham created a he has drawn a plot by considering the temperature in the x-axis and the standard. See the picture in page number 11. Okay, he had drawn a map, okay, graph, okay, by considering the temperature in the x-axis. X-axis the temperature 0, 200 degrees Celsius, 400, 600, 800, 1000, 1200, 1400, 1600, like that. The temperature is denoted in degrees Celsius. Okay, the temperature is denoted in degrees Celsius, and further it is in x-axis. Okay, what is in y-axis? The standard free energy change, that is the Gibbs free energy change, del G not equal to RT ln P. Okay, RT ln P by Kj mole inverse. Okay, that is taken in the minus RT ln Kp is taken in the that y-axis. Okay, so the resultant plot is a straight line. The resultant plot is a straight line. See, the resultant is a straight line. Okay, that red line you are seeing. Okay, that is a straight line which is denoted del S as a slope. Okay, del S is the slope and del H as a y-intercept. Okay, del S as a slope, del H as a y-intercept. So this graphical representation of variation of standard Gibbs energy reaction forms the various metal oxides. Okay, that is called the Ellingham diagram. Okay, this is a graph showing the temperature dependence of the stability for compounds. Okay, this analysis is used to evaluate the ease of reduction of metal oxides and sulfides. Okay, reduction of metal oxides. For reducing the metal oxides, this Ellingham diagram is used in the form of a graph. Okay, it was constructed by Harold Ellingham in 1944. Constructed by Harold Ellingham in 1944. Okay, in metallurgy, it is used to predict, for what it is used? To predict the equilibrium temperature between the metal. Okay, temperature between the metal, equilibrium temperature between a metal and its oxides and oxygen and by extension. Okay, and the reaction of metal with sulfur, nitrogen and other non-metals. Okay, reactions of a metal with sulfur, nitrogen and other non-metals. Okay, in metallurgy, it is used to predict the equilibrium temperature between a metal, its oxides, oxygen and by extension of reactions of metal with sulfur, nitrogen and other metals. Okay, this is the Ellingham diagram. Okay, this analysis is used to evaluate the reduction of metal oxides. Do you understood? Now see the diagram. Okay, it is also in your book. Okay, now in the y-axis, okay, del G equal to RT ln P. Okay, based upon the temperature. Okay, based upon, by plotting the temperature, we are calculating the del G. Okay, By increasing the temperature, the del G value is also increased. Okay. Let's see what are the observations we will get from this Ellingham diagram. Okay. Right. See, in y axis there are negative values. The 0 is on the top. See, the temperature, the 0 value is in correct place, but in del G value all are minus values. Minus 1200, minus 1100, minus 1000, minus 900, like that up to 0. 0 is on the top. So, there are more negative values. Okay. Okay, let me tell you the observations of the Ellingham diagram. Okay. See here, del G equal to del H minus T del S. Okay. Del G is the Gibbs free energy, del H is the change in enthalpy, T is the temperature, del S is the entropy change. Okay. If del G is less than 0 or it is a negative, means the reaction is spontaneous. Okay. I already told you that this thermodynamic principle of metallurgy is based upon what? Spontaneous. It is a spontaneous reaction. It is not a non-spontaneous or it is not an equilibrium. It is full of spontaneous. Spontaneous means continua nadandukitte irukum. Okay, it is spontaneous. Okay, so the values are negative, isn't it? The Gibbs free energy in the previous graph, you see the negative values are more. So if that is a negative, means the reaction is spontaneous. Reaction is spontaneous. Okay. If the del G value is greater than 0 or it is full of positive, means the reaction is non-spontaneous. The reaction is non-spontaneous. Okay. If del G equal to 0 means the reaction is at equilibrium. Okay. Del G equal to 0 means the reaction is at equilibrium. Okay. And for del H is negative. Del H is negative for oxidation with O2. Okay. Del H is negative for oxidation with O2. For del S is positive at high temperature, T del S value increases. T del S value increases. So, minus T del S in equation 1 becomes more negative. Okay. More negative. So, del G value becomes more negative, the reaction becomes spontaneous. Do you understood? Minus del ds value becomes negative, hence del G value becomes negative. If it becomes negative, the reaction becomes spontaneous. The reaction becomes spontaneous. Okay. If it is very spontaneous, we have to find del G. We have to find change in energy. Okay. Negative means change in energy. So, we have to choose a suitable reducing agent for what? To extract the metals from their oxides. Okay. It is done in a thermodynamic principle of metallurgy. The salient features of Ellingham diagram. Okay. Okay, what are the observations happen here, like that we will see. Okay. So, for most of the metal oxide formation, the slope is positive. Okay. Most of the metal oxide formation slope is positive. Okay. It can be explained as oxygen gas is consumed during formation of metal oxide, which results decreases in randomness. Hence, del S become negative. Del S become negative. T del S is positive in straight line equation. T del S is positive in straight line equation. Okay. Now, the graph for the formation of carbon monoxide is a straight line. See the picture in the graph for carbon monoxide CO. The 300, minus 300 and minus 200 between, there is a straight line coming. No, you are watching? Yeah, that is the CO. That is the carbon monoxide is acting as a reducing agent. That is a straight line with a negative slope. So, in this case, the del S is positive as 2 moles of carbon monoxide gas is formed by the consumption of 1 mole of oxygen gas. So, it indicates that CO is more stable at higher temperature. CO is more stable. Carbon monoxide is more stable under higher temperature. Okay. So, as the temperature increases, generally the del G value for the formation of metal oxide become less negative and become 0 at a particular temperature. So, below this temperature del G is negative and the oxide is stable, and above this temperature del G is positive. Okay. At the place 0 it becomes equilibrium. So, below 0 it is negative and above 0 it is positive. Okay, this general trend suggests that metal oxide becomes less stable at higher temperature. Okay, by this Ellingham diagram, we came to a conclusion that the metal oxides become less stable at higher temperature. Okay, what is the conclusion here? Metal oxide become less stable at higher temperature and their decomposition becomes easier Okay, then there is a sudden change in the slope at a particular temperature for some metal oxides like MgO, HgO. Okay, there is a sudden change in the slope at MgO, HgO. Okay, see minus 1200 and minus 100 between there is MgO, and minus 100 and 0 between there is MgO, HgO. Okay, there is a sudden change in the slope at a particular temperature for some metal oxide. So, this is due to phase transition. This is due to some melting or evaporation happens there. Okay. Let us see the salient features. The straight line represented by the function del G naught in the diagram represent the relative stability of oxides. The straight lines, okay, the straight lines are representing the relative stability of oxides. Okay, it is possible to visualize directly the affinities of metals from oxygens in their standard conditions. Okay, and it is possible to identify that there are easily reducible oxides of gold, silver, mercury. There are other oxides of greater stability such as FeO, P2O5, MnO, etc. and refractive oxides which are very difficult to reduce such as ZrO2, Al2, O3, CaO, MgO, etc. Okay. It is possible to identify the easily reducible oxides of greater stability and refractive oxides. Okay. So, these are the salient features of Ellingham diagram. Now, what are the applications of Ellingham diagram? Okay, what are the applications? Okay, this Ellingham diagram helps us to select a suitable reducing agent. Okay, this Ellingham diagram helps us to select the suitable reducing agent. எந்த reducing agent use பண்ணா நமக்கு metal ஈஸியா கிடைக்கும் அப்படிங்கறத நமக்கு சொல்றதுக்கு தான் Ellingham diagram நம்ம choose பண்றோம். Okay, appropriate temperature, which reducing agent, like that. So, we can calculate easily by this Ellingham diagram. Next, the reduction of metal oxide to its metal can be considered as a competition between the element used for reduction and the metal to combine with oxygen. So, if the metal oxide ரொம்ப stable இருக்குனா, then oxygen remains with the metal. If the metal oxide of element used for reduction is more stable, then the oxygen from the metal oxide combined with the element used for the reduction. So, from the Ellingham diagram, we can infer the relative stability of different metal oxides at given temperature. Okay. First of all, this Ellingham diagram for the formation of Ag2O and HgO is upper part of the diagram. Okay, it is in the upper part of the diagram. See the diagram, Ag2O, that is silver oxide, and HgO, that is mercury. Okay, mercury oxide, that is in the upper part of the diagram, and their decomposition temperatures are 600 and 700 Kelvin. Are you watching? Okay, that indicates that these oxides are unstable at moderate temperature. These are unstable. So, it will decompose on heating in the absence of reducing agent. If there is no reducing agent, okay, reducing agent illamaye idu decompose ஆகிறது. What is that? Silver and mercury. So, they are unstable at moderate temperature. So, they are in the uppermost edge in the diagram. Okay. Next, this Ellingham diagram is used to predict the thermodynamic feasibility of reduction of oxides. Okay. This Ellingham diagram is used to predict thermodynamic feasibility of reduction of oxides of one metal by another metal. Any metal can reduce the oxides of other metal that are located above it in the diagram. For example, in the Ellingham diagram, you see for the formation of chromium oxide lies above that of aluminium, meaning that aluminium is more stable than chromium. Okay, the diagram, See, aluminium, okay, aluminium, chromium oxide வந்து aluminum oxide க்கு மேல இருக்கு. இதிலிருந்து என்ன மீனிங் அப்படின்னா Al2O3 அலுமினியமோட ஆக்சைடு வந்து more stable than chromium oxide. So aluminum can be used as a reducing agent for reduction of chromic oxide. Okay, so we can use aluminium as a reducing agent for reduction of chromic oxide. So however, it cannot be used to reduce the oxides of magnesium and calcium, which occupy lower position than aluminium oxide. Okay. Next, the carbon line cuts across the lines of many metal oxides and hence it can reduce all those metal oxides. See, there is a carbon line at the center, minus 400 degrees Celsius. That carbon line cut across the lines of many metal oxides, isn't it? It is cutting across many metal oxides, minus 400 also, and at minus 200 and minus 300 there is a line 2C plus O2 that is cutting many metal oxides, isn't it? Hence, it can reduce all those metal oxides. Okay, carbon can reduce many metal oxides. புரியுதா? So, கார்பன் வந்து எல்லா மெட்டல் ஆக்சைடு வழியாகவும் பாஸ் ஆகி வருது. ஸோ இதுலேருந்து என்ன தெரியுது அப்படின்னா கார்பன் வந்து கார்பன்கிற ரெடியூசிங் ஏஜென்ட்டை நம்ம யூஸ் பண்ணோம்னா இந்த குரோமியம், மேங்கனீஸ், அலுமினியம், ஓகே, CaO, calcium, copper, இது எல்லாத்தையும் அது கடந்து வருது. So, we can use carbon as a reducing agent for many metal oxides. Okay. Do you understood? We came to a conclusion that carbon can be used as a reducing agent for many metal oxides at higher temperature. Okay. So, let us analyze thermodynamically favorable condition for reduction of iron oxide by carbon. Okay. Okay. For iron carbide by carbon, what happens there? Okay. If carbon is heated with oxygen, what gives iron oxide? We will get. Then we are doing iron oxide, we are heating it, and further what happens? Iron is liberated. So that metal we can get. Okay, that metal we can get. In this way, carbon is used as a reducing agent. So this Ellingham diagram for the formation of iron oxide and carbon monoxide intersects around 1000 Kelvin. So in 1000 Kelvin it is intersecting. Okay. So below this temperature the carbon line lies above the iron line. So the carbon line lies above the iron line, so which indicates that iron oxide is more stable than carbon monoxide. Okay, that indicates that iron oxide is more stable than carbon monoxide. So hence at this temperature range the reduction is not thermodynamically feasible. The reduction is not thermodynamically feasible. However, above 1000 Kelvin this carbon line lies below the iron line, hence we can use coke as a reducing agent. We can use coke as a reducing agent. What is a coke? Carbon is a coke. Okay, so we can use carbon as a reducing agent. Okay. Now the limitations of Ellingham diagram. Okay, in each and every diagram or every process there is not only applications or usefulness, there are also limitations. In each and every product there is a limitation. Limitation means disadvantages. Okay, what happens? See here, it does not tell anything about the kinetics of the reduction process. Okay, does not tell anything about the kinetics. Okay, kinetics means what? Motion. Okay, so it does not tell the kinetics of the reduction process, and the concept is based on del G naught, whose value is calculated from K, from the relation del G naught equal to minus RT ln K. So it has presumed that all the reactants and products are in equilibrium, but it is not always true. Okay, and the reactants and products may be solid. So at room temperature activation energy of reaction is high and reaction may not occur even del G is negative. Do you understand? It is constructed based upon thermodynamic considerations. Okay, it gives information about thermodynamic feasibility of a reaction. It does not tell anything about the rate of the reaction. Moreover, it does not give any idea of the possibility of other reaction must taking place. Okay, do you understood? Now the interpretation of del G is based upon the assumption that the reactants are in equilibrium with the products, which is not always true. Okay, do you understood? These are the limitations of Ellingham diagram. Now electrochemical principle of metallurgy. Till now we have seen about the thermodynamic principle of metallurgy. Now we are going to see about the electrochemical principle of metallurgy. Okay, what is electrochemical principle of metallurgy? Okay, it is similar to the thermodynamic principles. Okay, it is similar to thermodynamic principles. Okay, electrochemical principles also find applications in metallurgical process. Okay, in metallurgical process, electrochemical principles are also finding application. Okay, the reduction of oxides of active metals such as sodium, potassium, etc. by carbon is thermodynamically not feasible. Do you understood? The reduction of oxides of active metals such as sodium, potassium. Okay, active metals such as sodium, potassium are not reduced. Okay, sodium oda oxide, potassium oda oxide எல்லாம் thermodynamically metallurgy மூலமா நம்மளால reduction பண்ண முடியாது. So, do you understood? Okay. So, such metals are extracted from their ores by using electrochemical method. So, thermodynamically which metals we are unable to do, we are using electrochemical methods for that metals, okay, such as sodium, potassium. Okay, so such metals are extracted from their ores by using electrochemical methods. Okay, in this technique the metal salts are taken in a fused form. Okay, metal salts are taken in a fused form in a solution. Okay, the metal ion present can be reduced by treating it with some suitable agent or by electrolysis. Have you heard about the process electrolysis? Okay, the metal ion present in can be reduced by treating it with some suitable reducing agent or electrolysis. Okay, that is del G equal to minus NFe, okay, where N is the number of electrons involved in the reduction process, okay. F is the Faraday constant, E naught is the electrode potential of the redox couple, So, here del G is the Gibbs free energy change, we already seen in the thermodynamic. Okay, so for electrochemical process the formula is del G naught equal to minus NFe. Okay, if E naught is positive, okay, E naught value, that in the formula E naught is given, no. So, if E naught value is positive, then the del G value is negative and the reduction is spontaneous. Okay, and hence the redox reaction is planned in such a way that the EMF of the net redox reaction is positive. When more reactive metal is added to the solution containing relatively less reactive metal, the more reactive metal will go into the solution. Okay, for example, copper plus silver is taken. Okay, copper plus silver is taken. Now it is converted to copper is went as a aqueous form. Copper went into a solution because it is a more reactive metal. Silver is a less reactive one. Do you understood? So, when a more reactive metal is added to a solution, which is containing less reactive metal, the more reactive metal will go into the solution. Okay, children? Do you understood? This is the electrochemical principle, the main principle of metallurgy. Okay. Now, for determining the electrochemical principle, there is a process named Hall-Héroult process. Okay. For thermodynamic principle of metallurgy, we have used Ellingham diagram. Okay. And for explaining electrochemical extraction of aluminium, we are using Hall-Héroult process. Okay. What is happening in the Hall-Héroult process? Okay. In this method, electrolysis is carried out. Okay. Okay. How it is carried out? It is carried out in an iron tank. Okay, iron tank which is lined with carbon. Okay, that carbon act as a cathode. Okay, now the carbon blocks are immersed in the electrolyte. electrolyte. Electrolyte is a solution, okay. Okay, that in that electrolytic solution, the carbon blocks are immersed, okay. Immersed, okay. Okay, next, a 20% solution of alumina obtained from bauxite ore is mixed with molten cryolite and taken in the electrolysis chamber. That electrolysis is a solution I told you, no. In that solution, 20% of alumina, 20% of alumina which is mixed with molten cryolite, okay. Both are mixed and taken in a electrolysis chamber, okay. About 10% of calcium chloride is also added, okay. What are the electrolytes added here? 20% alumina and molten cryolite, 10% calcium chloride. These are mixed and added to the solution, okay. Now, we are immersing the carbon blocks inside. We are immersing the carbon blocks inside, and this method is carried out in an iron tank, and iron tank is lined with carbon, okay. Do you understood? Now what happens? The calcium chloride, okay. The calcium chloride, the 10% solution which we are adding, that calcium chloride helps to lower the melting point of the temperature mixture, okay. It is helping, calcium chloride is helping to lower the melting point, okay. Now, the fused mixture is maintained at about 1217 Kelvin, okay. 1217 Kelvin. Okay, now the process is going on, okay. Now the process is going on. The reaction is happening at anode, reaction is happening at cathode. Finally, we will get molten aluminium. Finally, we will get a metal molten aluminium. Okay, what happens here? Aluminium oxide is converted to aluminium. Okay, the process is reduction of metal oxides to metal. So, aluminium oxide is converted to a molten aluminium, okay. Okay, do you understood what happens in the Hall-Héroult process? In the Hall-Héroult process, aluminium metal is obtained by electrolytic reduction of aluminium. Okay, so pure alumina melts at over 2000 degrees Celsius, okay. So that melting temperature, so to produce that electrolyte at lower temperature, alumina is dissolved in molten cryolite at 1000 degree Celsius. This electrolyte is placed in a iron tank which is lined with a carbon, that is a graphite, okay. Okay, now the vat serves as a cathode, vat served as a cathode, carbons are anode. Okay, the oxygen produced at the anode react with them, okay, which forms carbon dioxide and carbon monoxide. Therefore, the carbon anodes are consumed and need to be replaced. Finally, what happens? Molten aluminium metal is produced at the cathode and it sinks in the bottom of the vat, okay. This is the Hall-Héroult process. Okay, see the reactions happening. Reactions at the cathode, 2Al2 which is in a melted form gives 2 aluminium, okay. Now at the anode what is happening? The oxygen which is melted and gives 3O2 plus 12 electron minus. Since carbon is acting as an anode, following reaction take place, carbon plus O2 gives carbon monoxide plus 2 electron minus, okay. Further, carbon plus 2O2 gives CO2, that is carbon dioxide. So, due to the above reactions, anodes are slowly consumed during the electrolysis. So, the pure aluminium is formed at the cathode and settles at the bottom. What happens? 4Al3, 3 plus, okay. What is that 3 plus 2E minus? They are the oxidation number which you have studied in your 11th standard, I think so. Okay, they are the oxidation number. Finally, we get the 4Al. Aluminium as a, okay, aluminium as a metal we are getting. That is molten alumina, okay. Now, refining process, okay. There are, in metallurgical process, there are main 3 processes: concentration of ore, the removal of impurities, extraction of crude metal, okay, conversion of metal oxides to oxides, and metal extraction, that is the metal extraction. Further, refining of crude metal, that is the 3rd process, refining of crude metal, okay. What is happening here? Let us see. Generally, the metal extracted from its ore contains some impurities, isn't it? Extracted metal, we have found extracted metal. Okay, aluminium oxide இருக்குனா aluminium oxideல இருந்து அலுமினியமை தனியா எடுத்துட்டோம். அந்த அலுமினியம்ல some impurities இருக்கும் இல்லையா? Okay, there will be some impurities in that extracted metals such as unreacted oxides. Some oxides are unreacted or other metals, non-metals எல்லாமே கலந்து இருக்கும். So removal of such impurities associated with that isolated crude metal is called the refining process. That is called the refining process. Okay, in this section let us discuss about some of the refining methods. Okay, distillation method. Okay, there are I think so up to there is 5 methods I think. Okay, I will tell you one by one. First one, distillation. Okay, distillation is there, liquefaction is there, electrolytic refining is there, zoned refining and vapor phase method. There are 5 methods of refining process. 5 methods in refining process. Let me tell you one by one. First of all, what is distillation? Okay, in this method, okay, this method is employed for low boiling volatile materials, okay, like zinc. Okay, zinc is boiling at 1180 Kelvin. Okay, zinc is boiling at 1180 Kelvin, mercury is boiling at 630 Kelvin. So that low boiling metals, no, zinc and mercury, like that metals, this distillation is used. Okay, in this method the impure metal is heated to evaporate the vapors and condensed to get a pure metal. Okay, for only heating is happening here for low boiling metals, low boiling volatile. Okay, low boiling volatile metals is heated and impure metal, that is a impure metal, no, that impure metal is further heated and the dust particles, everything is vapored and evaporated and finally it is condensed to a pure metal. Okay, that is distillation. Now what is liquefaction? Okay, it is employed to remove the impurities with high melting points. Okay, distillation for low melting point, low boiling point, and liquefaction for high melting point from metals having relatively low melting points such as tin, lead, mercury, bismuth. Okay, in this process crude metal is heated to form a fusible liquid. Okay, crude metal is heated and it is allowed to flow on a sloping surface. Okay, the impure metal is placed on the sloping earth of a furnace and it is heated above the melting point. Okay, in the absence of air, heated above the melting point in the absence of air, no air. Okay, without air that impure metal is placed on the furnace and heated above the melting point. Now what happens? The molten pure metal flows down and the impurities are left behind. Pure metal flows down, impurities are left on that furnace itself. Now the molten metal is collected and solidified. Okay, this is the process in liquefaction. Now what is electrolytic refining? Okay, electrolytic refining, the crude metal is refined by electrolysis. Okay, crude metal is refined by electrolysis. Okay, it is carried out in a electrolytic cell containing aqueous solution of salts of metal of interest. Okay, the rods of impure metal are used as anode and thin strips of pure metal are used as cathode. See in the picture, there is a cathode and there is a anode. Okay, in anode impure metal is placed, in cathode pure metal stripes are placed. Okay, the metal of interest dissolve from anode and pass into the solution. Okay, while the same amount of metal ions from the solution will be deposited at the cathode. So during electrolysis process, less electropositive impurities in the anode is settled down and removed as anode mud. Okay, here see electrolytic refining of copper. Okay, the electrolyte is a solution of acidified copper sulfate. What is that solution? Acidified copper sulfate. Anode is a impure copper. Okay, anode is a impure copper, cathode is a pure copper. Okay, cathode is a pure copper, anode is a impure copper. Okay, we can take anode as a impure silver rod, cathode as a pure silver rod. Okay, for that the solution will be silver nitrate and here the electrolyte is copper sulfate. Okay, when the current is passed through the electrode, further reaction taken place and the pure, what happens during electrolytes, the anode at the what happened here, copper atoms lost electrons and this enter the solution. Okay, the positively charged copper cations migrate towards the cathode and get discharged by gaining electrons and deposit on the cathode. Okay, metals such as copper, zinc, silver, etc. can also be refined in this process. Okay, pure metal is gained. Okay, pure copper we can gained. Cathode and anode act as a pure metal and impure metal. So, on passing the electric current, pure copper is deposited on the cathode. Pure copper is deposited on the cathode. Do you understood, children? Now, what is zone refining? What is zone refining? Okay. Right, this is the method. It is based upon the principle of fractional distillation. It is based upon the principle of fractional distillation. When an impure metal is melted, okay, impure metal is melted and allowed to solidify, okay. Impure metal is melted and allowed to solidify. What happens? The impurities will prefer to be in the molten region, okay. Means that the impurities are more soluble in the melt than in the solid state, okay. So, in this process the impure metal is taken in the form of rod. Impure metal is taken in the form of rod. One end of the rod is heated using mobile induction heater, okay. When the heater is slowly moved to the other end of the pure metal crystallizes, while the impurities will move to the adjacent molten zone due to the movement of heater. So, as the heater moves further away, the molten zone contains impurities also moves along it. So, this process is repeated several times, moving the heater in the same direction again and again to achieve the purity. Okay, heater is moving again and again to achieve the purity. Okay, see the picture. This is the, there is a germanium rod, there is a circular heater, okay, circular heater. That circular heater is moving here and there, here and there, here and there. For what? For increasing the purity level, okay. This process is carried out in an inert gas atmosphere to prevent the oxidation, okay. If oxygen comes here, what happens? Metal will become oxidized. Isn't it? So, for preventing that oxidation of metals, it is carried out in the presence of inert gas, okay. Elements such as germanium, silicon, gallium, okay, they are used as a semiconductor in the refining process, okay. See here, the difference in solubilities of impurities in molten and solid state of metal. Semiconductors like germanium, gallium are used, okay. Elements of very high purity are obtained, okay. Very high purity are obtained by this method. The circular heater is moving here and there, okay. When the heater slowly move to the other end, pure metal crystallizes. Then the impurities move to the adjacent mole. Impurities will move to the adjacent side due to the movement of heater. So, wherever the heater moves, the impurities will go to the adjacent side. In this way, we can increase the what? We can increase the purity level, okay. So, metals like germanium, silicon, gallium are used in this process. Do you understand, children? Now, vapor phase method, okay. In this refining process, the metal is treated with a suitable reagent. Metal is treated with a suitable reagent, okay, which can form a volatile compound, okay, with the metal. So, then the volatile compound is, when the volatile compound is decomposed to give the pure metal, we can understand this method by considering the following process, okay. We can consider it by the following process, okay. There are two processes, Mons process for refining nickel and Van Arkel method for refining method, okay. Mons process, Van Arkel method, okay. Right, first of all, Mons process, okay. See the Mons process. Here is we are taking impure nickel, okay. We are taking impure nickel, okay. It is heated in a stream of carbon monoxide at around 330 to 350 Kelvin. We are heating, okay. impure nickel is taken, carbon monoxide as a reduction agent we are taking, and we are heating, okay, heated in a stream 330 Kelvin to 350 Kelvin. What happens? The nickel reacts with carbon monoxide to form a highly volatile nickel tetracarbonyl. Nickel tetracarbonyl. Okay, the solid impurities are left behind. Solid impurities are left behind. On heating nickel tetracarbonyl around 460 Kelvin, 450 to 470 Kelvin, what the complex, okay, what is the complex? That complex is the nickel tetracarbonyl. That nickel tetracarbonyl on further heating, it becomes nickel, a pure nickel, and carbon monoxide is liberated as a gas. Okay. Now, pure nickel is formed by the Mons process. Okay. Mons process is a very important question. Okay. Vapor phase method. Okay. You have to study it properly. Vapor phase method and electrolytic refining. Okay. These are the most important questions. Okay. Next, Van Arkel method. Okay. For zirconium or titanium. In this method, it is based upon the thermal decomposition of metal compounds, which leads to the formation of pure metals, such as titanium, zirconium. Okay. Now, we are taking the impure titanium, which is heated with iodine, at 523 Kelvin. We are getting titanium tetraiodide, which is further heated at 1700 degree Kelvin. We are getting pure titanium, and iodide is left behind. Iodine is left. Further, we are taking what? Zirconium, isn't it? Yeah, zirconium is taken and it is heated with the iodine. Zirconium is heated with the iodine. Okay. What comes? Zirconium tetraiodide is formed. Further 1800 degree Kelvin we are heating, pure zirconium metal we are getting. Okay. This is the process of refining. These are the refining process. Do you understood, children? Right. Now, there are many applications of metals. Okay. Applications of aluminium, applications of zinc, applications of iron, okay, applications of copper, applications of gold. Okay, you study it. Okay, in page number 17 and 18 there are lot of applications. Okay, in which field aluminium are used, in where zinc are used, where iron is used, where copper is used. Okay, study it thoroughly. Okay, it is a important questions. Okay, it will come in a 5 mark. Okay, so you have to study everything. Applications of, this is the study homework for you. Okay, this is the studying homework. Applications of metals. You have to study the applications of aluminium, applications of zinc, applications of iron, applications of copper, and applications of gold. Okay, these are your homework. Study it thoroughly, and you can make one word from this topic also. Okay, okay, children, that's all today class. We have completed one unit. Okay, we have completed one unit. Okay, you study the first unit thoroughly. Okay, okay, mark the one words and everything by yourself. Okay, 2 marks everything I have taught you. Okay, study well. Okay, children, now it's time for your homework. Okay, write 10 words from the topic. Page number 10 to 18. Page number 10 to 18. Write 10 one words and submit it itself today. Okay, and there are assignment I am giving electrolytic refining process. That is the assignment for you. Hall-Héroult process and Ellingham diagram is for classwork. Okay, Hall-Héroult process, Ellingham diagram is your classwork. Okay, write it. Okay, take your own time. Okay, and write it. Okay, 10 one words you have to submit today, and the applications you have to study it today itself. Okay, there will be exam conducted online also. Okay, so you have to be well prepared. Okay, each and every day which homework I am giving and which things I am telling you to study well, you have to study it on the day itself. Okay, children, study well. Okay, you should be very curious about your exam. Now you are in the 12th standard of your life, which is the most important period of your life. Okay, so don't waste your time and study well. Okay, okay, children, thank you.